All right, we're going to talk about three important divisibility results, and again, we're going to call them theorems. So remember, in mathematics, a theorem just means a general result you can prove is always true, and that's what we're going to do. So the first result we're going to talk about is the following. And I think it's a good idea if you guys pause the video now and read this and see if you can come up with some English sentences that describe what this is saying. It might take a couple of minutes. I can start you off. So remember, these are whole numbers. So you can say something along the lines of, for whole numbers, A and B. And again, this symbol here means is a factor of. So you'd write something like, if A is a factor of B, then, and keep going like that. So pause the video now and see if you can figure out what this is saying. It's not a tricky part, but see if you can come up with a good way of saying the end bit here. Okay, so the way I would word this, and of course there's more than one way to word it, I would word it as follows. For whole numbers A and B, if A is a factor of B, then, well, what is this saying? This is saying that A is going to be a factor of B times C. And if I multiply B by another whole number, I get a multiple of B, right? That's what a multiple is. You take B and you multiply it by whatever. B times 1 is B, B times 2 is 2B, B times 3, it's like a times table. It's all multiples, right? So what this is saying here is that A is going to be a factor of B times anything. So it's going to be a factor of any multiple of B. So then A is a factor of any multiple of B. So that's what this is saying. Let's explore this a little bit. Let's see if we can make some sense. And sometimes it's a good idea to do a few examples. It doesn't prove anything, but it might give you the idea of what's happening. That's called inductive reasoning, when you're just doing a few examples. You can't prove something, but it might give you a general flavor of what's going on. In order to prove it, we'll have to use deductive reasoning. Okay, so let's go ahead. So let's do an example. Let's pick an A, B, and C that fit this situation. So it says here A is a factor of B, so I'm going to pick A to be A and B so that A is a factor of B. So let's do, let's say A is 3, and then B is going to be 6. 3 is a factor of 6, since 3 times 2 equals 6. Okay, and C can be any number, so let's make C 4. That will do. So let's draw this out. So if 3 is a factor of 6, what does that mean? Well, I should be able to write 6 as 3 times something, and of course it's 3 times 2. So I'm going to draw that as a little array diagram here. So we have 3 times 2. That's 6 dots. Here are my 6 dots. So 3 is a factor of 6 here. And we want to say 3 is a factor of 6 times 4, which is 24. So if it's a multiple of 6, then we're just going to add copies of these 6 dots to this diagram and show that we can still draw it as a rectangle where one of the dimensions is 3. So that's pretty easy. We'll just draw 3 more copies. There's 1 copy. That's 2 6s. That's 3 6s. And that's 4 6s. Awesome. There is my 6 times 4. So you can see what's going on here. We just have 4 times 2. So now we have 8 rows here. And we still have this 3 as our horizontal dimension. So that's what's going on here. So all we're saying is you can glom on extra copies of 6, and you can still, of course, write that number as 3 times some other number. So this is our example that we're going to kind of use as a model to see how to prove this. Okay, let's go ahead and do it. Remember, to prove things, you need to assume the if part is true and show that the then part must be true. So let's assume that the if part is true. So let's assume that A is indeed a factor of B. So what does that mean algebraically? So that means that we should be able to write B as A times some number. And I don't want to use C as that other number because C is going to stand for our multiple here. So I'm going to call it, I don't know, N, I guess. So B equals A times something for some whole number N. So that's what we're saying here. So in our little diagram here, our A is 3, our B is 6, and our N is just that other dimension, or vertical dimension, 2. We don't really care about it, but we know it's some number. All right, and the second part, let's mark down what we want to show. We want to show that A is a factor of B times C, which means that we should be able to write B times C as A times some whole number. So whatever we get here should be a whole number. Okay, so that's what we want to show. All right, and the information that we need to use in order to show that is our assumption, which is B equals A times some number. So this is the information we have, and we want to see if we can get it in this form. This should be the last line. Okay, so now we do a little bit of thinking. And this example that we did is a good kind of blueprint for how the general proof will go. Because if you think about it, there is nothing special about 3, 6, or 4. The only kind of important thing was that A was a factor of B. But if I wanted to, I could pick something along the lines of 5, 15, and 2. And I could draw this diagram the same way, except I would have a 5 by 3 rectangle here, and I would just join 2 of them together instead of 4. So the numbers aren't important, but let's think about what's going on with the idea. So all I did here was I took this guy and I glommed on 4 more. So I multiplied by 4. And what's 4? 4 was my C. So that's what I'm going to do. I'm going to take this equation, I'm going to multiply it on both sides by C. And you can see, if I have this, I want to make it look like this. Well, I would need a C on this side, so I guess I'll multiply by C. So let's do that. So let's consider B equals A times N. Okay, I'm going to multiply on both sides by C. So I get B times C equals A times N times C. And kind of this is how it looks now, since I just multiplied by C. But remember, multiplication is associative. So I can group these however I like. So B times C is the same as A times N times C, or I group the N and the C. And that's what's kind of going on here, right? All we're saying is when we glom on these 4 copies of 6, because it's like 6 times 4, so this is a multiple of 6 since we're glomming on multiple copies of 6. All we're doing, this new dimension, is just 4 times the old dimension. So it's 4 times 2. So our, what do we want to say here? Our C is 4, and our N is 2. So that's all that's going on. This is a by N times C rectangle now. And there, here's my A, here's my N times C. And how big is this rectangle? How many dots does it contain in total? Well, it contains B times C. So that's what's going on. But we know what we needed to show. We needed to show that B times C is A times some whole number. N times C, well, multiplication is closed in the whole numbers. If I multiply these, I get another whole number. So we can say, since the whole numbers, that set is closed under multiplication. I'll just write the multiplication symbol here. Close under multiplication. We know that it must be the case that A is a factor of BC, since we wrote BC as A times some whole number. That's what it means to be a factor. So we have A is a factor of B times C. And we're done. And mathematicians, for whatever reason, like to put a little white box when you're finished the proof, so I'm going to do that. You don't need to do it yourself, but if you're reading a mathematics textbook and you see that, that just means the proof is done. All right, so let's look at the second theorem now. The second theorem says, all right, if we have A being a factor of B and A being a factor of C, then A is a factor of B plus or minus C. So if we wanted to write this in words, you would say if A is a factor of, you could even say of both B and C, then it is also a factor of their sum or difference. All right, so that's what we mean there. Again, you can see the power of this notation, right? This is a lot cleaner to read than the English is. If you're happy with what this symbol means, then this is a lot cleaner and simpler to read than it written out in English. So I think this is a good time for you guys to pause the video and see if you can come up with an example that shows this. So do kind of the same thing that we did for Theorem 1. Pick an A, a B, and a C that satisfies this. So you want A being a factor of B and A being a factor of C. And see if you can draw a diagram to show that A is a factor of, let's just do the sum first, the factor of the sum, B plus C. When we prove it, the algebra will be pretty easy with the minus, but for the diagram, let's just work on the plus. So pause the video now and see if you can work that out. Okay, so I'm sure lots of people have various examples. I'm going to pick one. I'm going to let my A equal 4. And I need two numbers that are multiples of 4, where 4 is a factor of those numbers. So let's let B equal 8 and C equal 20. And you can see, well, 4 is definitely a factor of 8. 4 times 2 is 8, so we can draw that out. So I'm going to draw out 8 dots. 1, 2, 3, 4, 5, 6, 7, 8, where one of the dimensions is 4, and the other dimension is whatever. But we'll write it in anyway, so it's going to be 4 times 2. So we're thinking of this as our other number. Okay. And finally, well, c equals 20, so we can do the same thing. Maybe I'll do this one in blue. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I can write 20 dots as a 4 by 5 rectangle. And I want to show that 4 is a factor of 20 plus 8, which is 28. So how would I add these things and still get a rectangle that has dimension 4? Well, I just glom them together. So let me do that. In fact, I'm going to do that using kind of the cut tool here. Let me see if I can do this. It's not going to be perfect, but hopefully it'll be okay. Look at this. There they are. I'll write in that 5 again. So there I go. There are 28 dots now. Here are the first 8. Here are the second 20. So we do have a rectangle that's now 4 by, in this case, 2 plus 5 is 7. So we kind of added those previous numbers from the other dimension to get the vertical dimension of the new rectangle. So hopefully that kind of makes sense. So when we say it divides the sum or the difference, that's what's happening. We're just glomming those two rectangles together. And the new other dimension is 2 plus 5, which is 7. This horizontal dimension still stays as 4. So that's the idea. Okay, so now let's write up a good proof of it, now that we have the idea. If you're so inclined, pause the video now and see if you can write the proof of this. Look back at the previous slide for Theorem 1 to get an idea of the flow of it, if you need that. But it's a good exercise. Pause it now and see if you can prove this. Okay, let's go ahead. So remember, the first thing, we're going to assume that the if part is true. So let's assume that A is a factor of B and A is also a factor of C. So what does that mean? Thus, that means we should be able to write B as A times some number. Again, let's call it N. In fact, I'm going to call it N1 because we're going to have two of these other numbers. And C is going to be A times N2. And I introduced N1 and N2. I better tell you what they are. For some, N1 and N2 that are whole numbers. So in our example case here, remember to say that 4 is a factor of 8 or 4 divides 8. We don't really care about what these numbers are. We just care that they exist. So in our first example, well, this is our N1 and this is our N2. Okay. So we want to show, we'll do the plus case first. So we want to show that A is a factor of B plus C. Well, what does that mean? Well, that means we should be able to write B plus C as A times some whole number. So if we get A times something in brackets, it ends up being a whole number, we're good to go. So again, using our example as a guide, remember, there's nothing, if you did a different example than 4, 8, and 20, it still probably worked, but this general idea of glomming those rectangles together is going to be the exact same. And that's all we're going to do. We're going to take these two numbers and we're going to add them together. So let's go ahead. So let's consider B plus C. So we're going to take those, we're going to write them in terms of their factors. And so B is A times N1, C is A times N2. So this is A times N1 plus A times N2. Here's my B. Where is this? Here. And here's my C. Okay. And again, we want to write this as A times some whole number. A times some whole number. So what we did here, this is kind of like when we wrote it like this. Here's our B, here's our C, so they're separate rectangles. But if we notice they have a common factor of A, well then we're kind of glomming them together to make one giant rectangle. So let's go ahead and do that. They both have a factor of A, so I'm going to factor that out. And looking at it algebraically, remember, I know what my answer should be, A times some whole number. So I know the form it needs to look in, so I know I should be able to have a factor of A in all of my terms. So let's go ahead, factor that out. We get A times N1 plus N2. And hey, we've done it. Remember, N1 plus N2, it's the sum of whole numbers, and the whole numbers are closed under addition. When you add two whole numbers, you get another whole number. So we're good to go. So we'll say, since the whole numbers are closed under addition, well, that means that A is a factor of B plus C. And we're done. Now the subtraction, we just have to be a little bit careful because we don't want to end up with negative numbers. To be completely honest, if we allow integers, which we'll talk about a little later, everything will be okay. This still all works with the idea of integers, but we're just limiting our case to whole numbers. But if you think of the algebra here, if we subtract things, maybe I use green actually, if we subtract things instead of adding them, we would need to show that A is a factor of B minus C. So B minus C should be A times some whole number. So let's consider B minus C. So that's just AN1 minus AN2. You can still factor out that A, so you get N1 minus N2. And then, well, the only thing you'd have to make sure of, because if you don't want to end up with negative numbers, we just have to add something in here that, in the subtraction case, we need that B is indeed greater than or equal to C. So when we do the subtraction, we don't end up with a negative number. But I do want to stress that if we allow integers, we don't have to make this assumption here. Everything would just work. And then down here, we could even just say instead, since B minus C is indeed, I'm running out of space here, I can just scroll up a little bit. Since B minus C is indeed a whole number, since B is not less than C, then A is still a factor of B minus C. So we're good to go in both cases. All right, so here is our final theorem, Theorem 3, and it's the case where A is a factor of B, but it's not a factor of C. Well, then this is saying that A isn't a factor of the sum or difference. And I do want to make a note here. We're going to do just the proof of the sum case here. We're not going to do the difference case. And the reason is that the idea is the same. They're just, you have to be a little more careful about remainders somehow, and it just gets a little fiddly, if you will. And kind of there's no new important ideas that are shown, so we'll just won't do that one. We'll only do the positive case, but we'll know that the subtraction case is true as well. So again, I think it's a really instructive thing for you guys to pause the video now and come up with an example. Find a situation where A is a factor of B, A isn't a factor of C, and see if you can kind of, using that rectangle idea, show that A isn't a factor of the sum. And just focus on the sum for now. Okay, so the example I'll do, let's make A equal 4 again. B will be 12, and C will be, well, we need a number C that 4 isn't a factor of, that's not a multiple of 4. So how about 7? That will do. So again, we want A to be a factor of B, and it is. B is 12, and 4 times 3 is 12. So let's write that as a little rectangle. There is our 12 dots. 4 times 3 is 12. C isn't a factor of 4. Let me do this in blue. Maybe I'll underline this first. So C isn't a factor of 4. So if we try and make it a rectangle with dimension 4, what happens is, well, we don't get a complete row here. We have this kind of remainder row, because if you divide 7 divided by 4, you get 1 remainder 3. You can have one group of 4 with 3 left over. So if we try and glom them together, well, what happens? Well, let's see. In fact, it's pretty easy to see what's happening here. In fact, maybe I'll write this before we do that. Let's write this as, we have this like 4 by 1 actual rectangle, and then we have kind of this remainder row. So I'll say remainder 3. And if we try and glom them together, I'll just write them in. That remainder row still stays as a remainder row. There's no leftover dots to fill it in. All the other dots are already grouped. The ungrouped dots are just hanging out there. So if I add the numbers 12 and 7, then that remainder just carries along for the ride. So that's what's going on here. So we still have this kind of 1 by 4 rectangle up here, the full row, but we still have those remainder dots, the 3 remainder dots left over. So you can see there's no way to fill in this row. So that's what's going on. Those remainders stay remainders. So again, this is going to be a little harder, but I think it's instructive for you guys. Try to prove this. So pause the video now. See if you can write down a good proof of this. Remember, I do want to stress one thing as a little hint. Remember that if A doesn't divide C, that means C equals A times some number n plus a remainder. And your remainder is going to be, well, it can't be 0 actually because it doesn't divide. So it's going to be between 0 and A. So you can always write a number that doesn't divide as some multiple plus your remainder. Like here, 7 we can write as 4 times 1 plus our remainder 3. So that should help you there. Okay, now that we're back, let's do our assumptions. So let's assume that A is a factor of B and A isn't a factor of C. And let's write what this means algebraically. Thus, we can write B as A times some number, let's say n1, for some whole number n1. Remember, this is saying n1 is an element of the set of all whole numbers. And, maybe I won't put that period, and C is going to be A times some number n2, but it doesn't divide, so we're going to have some remainder R. And they're going to be whole numbers for R and n2 that are whole numbers. But there's an extra condition with R. R is a remainder. So R has to be greater than 0. And since we're grouping things in groups of size A, then it has to be less than A, because it got to be the ones you were unable to group. If you had A or more, you could make a group of them. So the remainder are the ones unable to group in groups of size A. In this case, A was 4. So that's our setup. So what do we want to show? We want to show we can write B plus C. Remember, we won't worry about the negative case. We want to show B plus C as A times some whole number plus a remainder. So if we can do that, then we're done. We've shown that A isn't a factor of B plus C. And again, our example here, or the example that you have, is instructive of how to do this. So we're going to take the B, we're going to take the C, and we're just going to add them together. And what happens is we're going to get this rectangle bit, that is 3 plus 1, so kind of that, here's our n1, here's our n2, so n1 plus n2 long, because we just glom them together, but the remainder just stays the same. It's just along for the ride. So that's our plan of action. And we're just going to, here's what B equals, here's what C equals, and we're just going to write that out algebraically. So let's go ahead and do that. So let's consider B plus C. We know B is A times n1, and C is A times n2 plus R. And maybe it's a good idea, I'm going to put brackets around these. They're not doing anything mathematically, but it helps people to see that B is A times n1 and C is A times n2 plus R, that they kind of go together. Okay, and again, I know how this needs to look. A times some number plus R. Now, I'm going to write this again without the brackets. And then we'll talk about, oh, that's not A, n2 plus R. I didn't like how my n2 looked, so I just rewrote it. I know how I need to make this look. I know this guy is already a remainder. So, in my final expression, I want this plus R at the end. I already have it. I'm not going to touch this. This is just going to stay around. Okay? And again, just like before, I just need to factor out that A, and that's kind of glomming these guys together. So let's do that. This is A times n1 plus n2 plus R, and we've done it. A times some whole number plus that remainder that doesn't go away. That is just stuck around. So let's just say that n1 plus n2 is a whole number, and we're good to go, since the whole numbers are closed under addition. We know that, and I should say, let me also say, just so it's very clear, and R is a remainder, so R is a proper remainder. It's not 0, and it's smaller than A. It's smaller than the size of our groups. Then we can say that A can't be a factor of B plus C. And we're done. And remember, the negative case is pretty much the same. It just gets fiddly because if we subtract, we end up with a new remainder. So if we subtract these guys, rather than having remainder 3, we'll have remainder 1. So it just gets a little fiddly, but the idea is the exact same. So the astute of you might have realized that, well, we've covered this situation where A is a factor of both B and C. We've covered the situation where A is a factor of one of B and C, but we haven't covered the situation where A is a factor of neither. So maybe it's a good idea for you guys to pause the video now and see if you can play around with some examples and ask yourself, is A a factor of the sum of these guys? So pick an A and then pick two numbers that aren't multiples of A and see what you discover. In fact, I will tell you, just to make your life a little bit easier, let A equal, let A equal 4. Let A be 4, B and C you're free to choose. Play around with it, do 2 or 3 examples, and then unpause the video. Okay, so I'm going to do a few examples here. A will be 4, let's let B equal 7, and let's let C equal, I don't know, 7 again. Okay, they can be the same number, it doesn't say they can't. B and C are the same number, that's fine. So, let's ask ourselves, is 4 a factor of 7 plus 7? Let's check. Is 4 a factor of 14? Of course it isn't. No. Since 14 is 4 times 3 plus a remainder of 2. If you divide 4 into 14, you get a remainder of 2. So maybe you're going to say, all right, well, it looks like it's always not a factor. But here's a situation where just one example isn't enough for you to see what's going on. Let's do a different one. Let's do A equals 4. In this case, B is going to be 7, and C is going to be 5. So 4 isn't a factor of 7. 4 isn't a factor of 5. So is 4 a factor of 7 plus 5? And of course it is. 4 is a factor of 12, since 12 is 4 times 3. So what this says is that if they both don't have A as a factor, B and C both don't have A as a factor, or A isn't a factor of B and A isn't a factor of C, then it could be either. You don't have, just off that, you don't have enough information to say whether A is a factor of the sum. So what we can say is that either situation can happen. So you don't have enough information to determine if A is a factor of B plus C or it isn't, unless you know something more about B and C. And what you'll need to know is something about the remainders. I'll give you if we were to talk about this more, it turns out if you add the remainders together and you get a multiple of 4, then you're good to go. It is a factor, and if you don't, it's not. So we won't get into that, but just know there's more to be said about this situation.